Okay. Yeah.
Go for it.
Could we go over chapter 14, introduction, question 9, and additional question 4?
Okay. So, chapter 14, introductory question
9?
9, and additional problem 4.
Yeah.
Okay. Introductory question 9. Oh, yes, angular momentum. So a 50-kilogram diver, let me just, because I know I'm going to have to do that, start the whiteboard. Because, let's face it, I'll be doing it soon. And 50-kilogram diver in a full layout position with a total body radius of gyration with respect to her transverse principal axis equal to 0.45 meter, leaves the springboard with an angular velocity of 6 radians per second. What is the diver's angular velocity when she assumes a tuck position, reducing her radius of gyration to 0.25 meters? Okay. Classic angular momentum question. Conservation of angular momentum. So I will share the whiteboard. And while I'm at it, I will get rid of the keyboard because let me just stop sharing there for a second. Not sure if that that's better. Yeah. Okay, so we are have a mass of a diver equals 50 kilograms. We have a radius of gyration when they take off of 0.45 meters. So that's just the distribution of it. And they have an angular velocity of 6 radians per second. So let's start with figuring out I. Radius of gyration squared. So that's going to be 50 kilograms times 0.45 meters all squared. So 50 times 0.45 squared. Anybody?
I have 10.125.
Yeah, I got the same.
Oh, good. That's very good. 10.125.
Yes.
Okay, yeah. And that'll be, of course, kilogram meters squared. And angular momentum equals I times angular velocity, which is going to equal 10.125 kilogram meters squared times 6 radians per second. And let's just remind people, this is chapter 14, introductory problem 9. So that's going to equal
60.75.
75 kilogram meters squared per second. Yeah. So there we go. That is how much angular momentum they have well in the air. We also noted here, very important, that the angular velocity was in radians per second, cannot be in degrees per second. You have to convert. These are one of these equations where you need to have the angular measure in radians because you need it to drop out. So it's going into an equation, so it needs to drop out. So they're in the air. That's how much angular momentum they have just after takeoff. Nothing's going to change that amount of angular momentum while they're in the air, but they can play with it. And one of the things you can do when you play with it is change your moment of inertia. Now, looking at that equation for moment of inertia, clearly while they're in the air, they're not changing their mass. I would hope that, that's not going to happen, but they could definitely change the radius of gyration, and that's in fact what they do. So everything is this, the mass is still 50 kilograms. And the radius of gyration is now after they tuck. Now, not surprisingly, when they tuck, the radius of gyration gets smaller, which is exactly what you would expect, because the tighter you are, the less distributed your mass is, and therefore the smaller your radius of gyration is. So I is now going to equal 50 kilograms times 0.25 meters squared, which is equal to
3.12.
3.12 kilogram meters squared. Okay. And, the other thing we have to remember is that radius of gyration has the larger effect in that equation because it is squared. So, angular velocity equals the angular momentum divided by moment of inertia, just rearranging the equation. So that is still going to be 60.75 kilogram meters squared per second. And it's going to be divided by, those will cancel. You'll be left with per second, and you're going to put that radians back in. So 30.75 divided by 3.12.
19.44.
Radians per second. So you get tighter, you go faster. A certain amount. Anybody have any comments or questions on this particular question? Again, unmute because I can't see chat while I'm in screen sharing.
Actually, I do have a question. Well, not necessarily a question, but a comment, because I did this problem, and when I got 60.75, I multiplied that with 0.25 squared. But I think now I understand my mistake, because the mass didn't change, because I think I substituted it with that.
Yeah.
That was a mistake.
Yeah,
okay.
The mass doesn't change, but it's in the equation, but it doesn't change.
Okay, thank you.
No problem. And in fact, if you had not even known what the mass was and just put in m here, and you would have ended up with 0.45 times 6, or 0.45 squared times 6 times m. And then when you came over here, you would have had 0.25 squared underneath times m, and the m's would have canceled. So the M doesn't play a role because it didn't change. But if you have it in the top part, you have to have it in the bottom part.
Right. Okay. Yes, I see that. Yeah.
Oh, okay. Any other questions on this one? Okay, let's clear the canvas, and we're going to go with, again, chapter 14, additional problem 4. And okay. We have a 7.27 kilogram shot making 7 complete revolutions during its 2.5 second flight. If its radius of gyration is 2.54 centimeters, 1 inch, what is its angular momentum? Okay, so we have a mass equals 7.27 kilograms. We have a radius of gyration equal to 0.0254 meters. And so we have I equals mass times radius of gyration squared, or 7.27 kilograms times 0.0254 meters all squared, which equals 0.254 squared times 7.27.
I got 4.69 to like the power of -3, 10 to the -3.
Well, that's quite believable, because 0.025 is to the 2 decimal places, and you multiply it to something. So it would be times 10 to the -4. And then when you actually multiplied it by something else, it maybe make it bigger again. So 10 to -3 would be actually quite reasonable for this kind of question where your radius of gyration is so small. So yes, that's quite logical. So now to find my angular momentum, I need I times, so moment of inertia times angular velocity, but I don't have an angular velocity. This is one of those questions where I told you back in the very first week of classes that things we learned in the first couple of weeks, we're still going to be coming back to in the last couple of classes. So we need to actually calculate the angular velocity. It didn't just give you the angular velocity, you have to calculate it. So think back to how you calculate angular velocity. And that's going to, so we need to have angular velocity equals a change in angle over a change in time. Does 7 complete revolutions in 2.5 seconds. So again, we can't put 7 revolutions divided by 2.5 seconds. We have to put 7 times 2 pi, because there's 2 pi radians per revolution, right? So that's how many radians it goes through in 2.5 seconds. So 7 times 2 times pi divided by 2.5.
I got 17.5.
Kind of seems about proximate because those, yeah, it'd be more than 2 times 7. So, hey. So, 4.69 times 10 to the minus 3 times 17.5. So that is going to equal, this would be kilogram meter squared.
Professor, can't we just use the, was it W is equal to H over I? Because we're given the angular momentum in this question.
Are you given the angular momentum?
I think so. Is it?
It asks for what the angular momentum is for question 4.
Yeah, question 4. Sorry, I got confused with question 3. Sorry about that.
Yeah, no, we don't know what angular momentum is, so we're calculating it.
Yeah, so I got 0.0825.
Now in this one, you might actually have more of a round off error just because of the, going down. So anyway, that'll be kilogram meters squared per second. Any questions on this one? Okay. Let's. Tanaz, I think you were next.
Yes. Okay. So I actually have 2 questions. So in chapter 14, the introductory problems, question 3, because it's asking for follow through, and I'm wondering how we can.
Okay, let's.
Wasn't sure about that.
So introductory problem through skilled performance of a number of sports skills is characterized by follow through. Explain the value of follow through in terms of the concepts discussed in this chapter. Well, I guess if you're following through, if you're following through, again, it's not really specific about a sport. I wouldn't ask you a question that was sort of this vague. But if you're following through, first of all, just from a pure injury perspective, as you release, let's say I'm doing a pitch, an underhand pitch, okay, and I would go through, and it would follow through. I would even after I released the ball, I would, my hand would still keep going. The ball would be now going off on a, straight ahead, because there's now nothing that's going to change its direction, other than gravity, because it's now a projectile. But but my arm is going to still going through. So think about it. My arm has angular momentum, right? So you need to stop it. You need to stop it. And it's torque times time, right, is going to change that angular momentum. So angular impulse, torque times time, is going to change the angular momentum. You need it to stop. If that stop occurs over a longer period of time, then the torque I need to stop it is less, right? So the angular momentum of my arm is going to be related to how fast my arm is going. And so if I'm trying to do something very fast, I'm going to have a fair amount of angular momentum that I have added to it over time as I've gone through the cycle. And now I have to stop it. And if I stop it quickly, so remember, torque times time. If time is small, that means torque has to be high. That torque is being given by muscles around my joints that are actually acting eccentrically because they're actually going to be stopping my arm and slowing down my arm. So think about that. You need to have greater strength to slow it down quickly than if you allow it to follow through and you're allowed to slow it down at a smaller time or a longer period of time. That's just safer, right? At a certain point, you either aren't going to have the strength to do it, in which case it's going to bottom out on you really quickly, which isn't healthy, or you're going to have to use 100% max strength in order to slow it down, which, if you're a pitcher, that's a recipe for overuse injury. So by allowing it to slow down over a greater period of time, you don't need as much torque, so it's going to reduce that risk of injury. Does that make sense?
Yes. Okay.
Good.
Sorry, I have like 2 more questions.
Yeah.
So with the additional problem, still chapter 14.
Yeah.
I did number 3, but my answer was really small. Like I followed all the formulas and I don't know what happened there. So was it possible that we?
So you want number 3, additional problem 3?
Yes, please.
Okay, no problem. So let's just share the old whiteboard. Actually, just before I share, need to check. Okay. Sharing the whiteboard. There we go. Chapter 14. Additional problem 3. A 0.68 kilogram tennis ball is given an angular momentum of 2.72 times 10 to the minus 3 kilogram meters squared per second when struck by a racket. If its radius of gyration is 2 centimeters, what is its angular velocity? Okay, so we have m equals 0.68 kilograms. Always a good thing to write down what you're given. H angular momentum is going to be 2.72 times 10 to the minus 3 kilogram meters squared per second. The radius of gyration equals 0.02 meters squared. This is meters squared in here, so you have to have meters here. You can't have left it as centimeters. And what they want to know is angular velocity. So let's start with I. I is going to equal m times radius of gyration squared, which is 0.68 kilograms times 0.02 meters all squared, which is
2.72 to the power of like 10 minus 4.
That sounds about right. And so we have, of course, angular momentum equals moment of inertia times angular velocity. Rearrange that. Angular velocity is going to equal moment of inertia, angular momentum divided by moment of inertia, which is 2.72 times 10 to the minus 3 kilogram meters squared per second divided by 2.72 times 10 to the minus 4 kilogram meters squared. Those are going to cancel, so we're going to be left with per second, which of course means we can put the radians back in. And that one is, I mean, those are going to cancel, so we're going to be left with 10. 10 to the minus 3 divided by 10 to the minus 4 would be 10 radians per second. Any questions?
Okay, I see my mistake. Thank you.
No problem. Any other questions, comment on this one? Again, just unmute. We're all good? Okay, clearing canvas. Did you have any more or?
Just one thing. So I did number 8, and I wanted to look back and see if I did it correctly, because I know in one of your tutorials you've actually did it for a student. But my question is that when you were writing down the formula, so I have it that FC, force equal by mr angular momentum squared. But then instead of the r radius, you put a. So I'm wondering why is, where is that a coming from? I'm not quite sure.
Well, it could have been it could have been just my writing, but let me just quickly go over it. A 7.27 kilogram hammer on a 1 meter wire is released with a linear velocity of 28 meters per second. What is the reaction force exerted on the thrower by the hammer at the instant before release? And of course, the centripetal force, which is the force the thrower is putting onto the hammer, and the centrifugal, which will be the opposite, the force the hammer is putting on the thrower, are equal and opposite. So the same, it will be the same amount, just opposite directions. But 7.2, that equals mass times the radial acceleration. I might have put that in, which equals mass times linear velocity squared over r. Is that what I did?
I think so. Okay.
Okay.
At first I was a little bit confused. I was like, where is that coming from? Okay.
Because that's what goes in there. That's why you have v squared over r, because that is it's just Newton's second law. Sorry. Okay, that solve that. Good. Anybody else have any questions on that?
Thank you.
Okay. Nicholas, I think you're up now.
Hi, Professor Moore. I just had some questions from like some of the previous chapters.
Yeah.
From chapter 13.
Mm-hmm.
Additional problems 4 and 10. I just didn't really know how to like do those two questions.
Okay, chapter 13, additional problem 4 and 10. I've never actually done 10, I don't think, in these ones. I've talked about it, but I'll go as far as I expect you to do in this problem. But 4, I love 4. 4 is a great question. 4 is a good what if question. Because we're so used to looking at things from the perspective of biceps that we forget, you know what, triceps gets used too. And this can be a triceps motion. Depends on how much force is on the hand. So it can go either way, which is why I always like this problem. So this is chapter, let's try a different color. I'm feeling chapter 13, additional question 4. And we have, always good to start with our free body diagram. We have our forearm and hand. And instead of like the usual weight that we might have in a hand, you know, you're holding a ball, you're holding a weight. In this case, the force, in which case the force would be going down, right? Because it would be the force of gravity of whatever it is we have in our hand. But now we're pushing down on something. So that means if we're pushing down on the scale is pushing back up on us. So this is the force of the scale, which we're told is 90 newtons. So we have our force of gravity, which is the weight. The way I often do it is it's a little different nomenclature that they use, but as I've said before, this is as long as it's logical. So it's the forearm and hand. Force due to gravity. We have the axis of rotation, or the center of the elbow. In this particular posture, the force of the triceps is going to be more proximal than the center of rotation. And that's actually what we are looking for. Now, we are also going to have our joint forces here, but they're acting right. FJ, Y, FJ, X, and this is E, the center of rotation, which of our elbow joint, and our reference frame. Those are the directions we're going to consider positive when we are creating our equations of equilibrium. So we know this is an equilibrium. They're pressing down on it. They're not moving. So it is a situation where we're in equilibrium, so that the sum of the forces in the x direction equals 0, because, well, basically equals mass times acceleration, and acceleration equals 0. Sum of the forces in the y direction equals 0, and the sum of the torques. And because it's an equilibrium, we can choose any point on our system to do this with. So we will go around the elbow equals 0, because alpha, the angular acceleration, also equals 0. So let's start with the sum of the torques. Well, we need some distances. That distance, which is the moment arm, because this is the arm is in a horizontal position. That means that the forces, the force of gravity and the force of the scale, are both acting straight vertical, which means they'll be 90 degrees. So however far they are, those forces are from the axis of rotation, which is the elbow, or the point that we are taking our torques around, which is the elbow, is going to be our moment arms because it's 90 degrees. So this is 17 centimeters. This is 32 centimeters. And this distance is 3 centimeters. So if we do our sum of torques, anything that causes this to rotate around counterclockwise, I will consider positive. Anything that would consider this to rotate around my elbow, and I literally would put this pen over top of my free body diagram. I would grab hold of it right where my elbow is, and then I would either push up where the scale is or push down where the gravity is and see which direction it actually rotates. So the sum of the torques around elbow equals 0, which equals, we have the scale's pushing up, so it's going to cause it to rotate counterclockwise. So it's going to be plus 90 newtons times 0.32 meters. If I push down on my here, it's going to cause it to rotate as long as I'm holding it over here at the elbow. If I push down here, it's going to cause it to rotate clockwise, which I consider negative. So it's going to be minus the 40 newtons. 40 newtons times 0.17 meters. And then this guy right here, if I push up on that on the other side, it's going to cause it to rotate clockwise also, because now I'm pushing up on this side. It would have the same effect as pushing down on this side. So it's also going to be negative. The force of the tendon times 0.03 meters equals 0. So the only unknown here is the force of the tendon, which is exactly what they ask you to calculate. So if I rearrange everything, I'm going to have 90 times 0.32 minus 40 times 0.17, all divided by, and those are all going to be Newton meters. I'm going to divide it by 0.03 meters, which therefore I'll be left with newtons, which is exactly what I want. And there you go. If somebody wants to plug it through and
733.3 newtons.
Yeah, good. So any questions on that?
Dr.
Yeah.
Moore?
That makes sense.
Yeah.
Because I think I'm not used to like triceps, so when I think biceps, I thought like it would be going in the positive direction, because like positive would be upwards. But yeah, this makes a lot more sense.
Again, it's torque, so it's which direction it rotates it, not whether it's pointing up or down.
Mm-hmm. Yeah.
Somebody else had a question?
Yes, I just have a question about the force at the joint.
Mm-hmm.
Do we not consider it because it's directly actually at the joint and the moment arm is 0? Is that
Yep.
right?
That's
Okay.
exactly right.
Thank you.
And so it's often in these kinds of questions that we calculate the torque. We look at the torque first, because then we don't have to worry about those forces. And then afterwards, we would look at the forces in the X and Y direction. And in fact, I mean, you can see that there's no other forces acting in the X direction. So the joint force in the X direction is going to equal 0. One of the things that I sometimes do with this question is try and figure out at what time, what is the limit? You know, I've sometimes talked about doing what ifs. And no, there isn't an answer for this. So you kind of, you're playing it on your own, but it does help you sort of picture it. I could have the triceps active here, or I could have the biceps. So if I had had a biceps, if instead of drawing a triceps, I had actually drawn a biceps, I would have in fact got a negative value for this, because when I rearranged it, so it would be the, if I did that, I would actually get exactly what you said you did with the tendon. You'd end up with a negative value here, right? And that's just not right, because you need to have a positive muscle force. But you can kind of sit here and go, so when it's triceps, it's positive. If you tried to pretend it was biceps, you would get the wrong answer, because you would get a negative. But I sometimes wonder what would happen, you know, how much force can I push on the scale and have neither biceps or triceps? I mean, you can actually rest your hand on the scale, right? There is a point where you switch over from biceps to triceps. So if I just lightly rested my hand on the scale, it actually would be biceps, till eventually I was totally relaxed on both biceps and triceps, and that would be it. And then I have to add more force in order for it to get to be the triceps. So if I wanted to look at the point where neither triceps or biceps were active, I would have, you know, the sum of the torques around the elbow equals 0. I would now have no muscle forces at all. So that is going to equal the force on the scale times 0.32 minus 40 newtons times 0.17. The mass of my my forearm and hand isn't going to change. It's equal to 0. So the force of the scale would be 40 newtons times 0.17 meters divided by 0.32 meters. I'm going to be left with newtons. So 40 times 0.17 divided by 0.32. Anybody?
21.25 newtons.
21.25 newtons. And again, this is not in the book. This is just me playing with the question so that I understand the role of biceps and triceps in this particular situation. If I had a recording of, if I just rested my hand on the scale, just relaxed and rested my hand on the scale, that is the value I would get on the scale, 21.25 newtons. If I had less than 21.25 newtons, so let's say 15 newtons, which muscle is active, the biceps or the triceps? Any thoughts, anybody? If I had less than 21 newtons, so 21.25 newtons is no muscles on. I'm just resting my arm on the scale. And you can picture that. You just relax, picture relaxing your hand on the desk. Be the same thing.
Okay, lifted biceps.
Yes, exactly. So if it's less than 21.25 newtons, it's the biceps that are active. I literally am holding my hand so that it's in contact with the scale, but I'm not putting the full weight of it down onto it. So if it's less than 21.25 newtons, the biceps would be active. If it's greater than 21.25 newtons, then I'm actively pushing down on the scale more than just gravity. And you can see the 90 newtons would be greater than 21.25. So anything greater than 21.25, the triceps are the muscle that's on, and I'm actively pushing down on the scale. Anything less than 21.25, I'm sort of partly taking up the weight of my forearm and hand with using my biceps. So does that make sense to everybody?
Yep.
Yeah, good. That's a good what if one. Okay. The next one you wanted was
Question
Chapter
10.
13, question 10. Okay. It is the tendon forces on the patella. So we have a patella. We have, oops, sorry. It's hard to do it on an angle like this, but I'll try. We have the force of the patellar tendon, which we're calling TB, tendon B, and it's at 30 degrees. And we have the force of the femur onto the patella, which we're calling F, and it's at 29 degrees to the horizontal. And we have the actual quadriceps tendon, and it's at 38 degrees. And that's what we're calling tendon A. Okay. It's in equilibrium where there's no motion occurring at the joint. That is code word for saying this is in equilibrium, right? When there's no motion occurring, we're pretty much at equilibrium. Other code words that we've talked about before are when slowly moving, things like that, where you can kind of picture, at least it's a quasi static situation where the accelerations would be so low as to be negligible. Certainly when it says no motion, you know this is an equilibrium situation where the some of the forces in the x direction, let's just decide which direction I'm going to call x is that way, y is that way, theta equals 0, sum of the forces in the y direction equals 0, and the sum of the torques around what point? You could take it around any point. Reality is you don't need to use torques in this one. So let's say at point any point. Let's call it the center of gravity of your you wouldn't use the center of gravity. You would use, if you wanted to do torques, you could, but you'd have to find some point like this point right here and call it point A. Sum of torques around A equals 0. I'm not going to go that route. Now, this question is not so hard to set up the equations of motion and the equations of equilibrium. And it is the equations of equilibrium that are the part that I've taught you, okay, that are coming out of this portion of this course. So what I would ever ask for something like this would just be that you could recognize how to set up the equations of equilibrium. To actually solve it, I wouldn't, because to solve it, you have to do something called substitution. And while it is not a hugely difficult concept, and I'm sure you've done it all before, in this particular question, it just has a lot of little numbers with sines and coses and stuff. And to keep them all, the idea that you could make a math error is pretty high. And it's not really it's not really testing you on the stuff we learned from the class. So I'm going to start with what I would expect from this class that you would be able to do. So each one of these has a y component and an x component. So this is t, oops, sorry, that's not a t. That didn't work very well. I'm just going to put them all in blue. So this is TBY, TBX, FY, FX, TAY, TAX. Okay, so let's just figure out what each of those are. TBY equals TB times, and it's adjacent to the 30. So cos 30, are we all good with that? And since TB equals 80, that equals
Uh, 69.28 newtons.
69.28 newtons. TBX equals TB times sine 30, because again, that would be the same as here, and that would be opposite. So 80 times sine 30, I believe, will be 40 newtons, because sine 30 is a half. So 80 times sine 30, which would be 40 newtons. Now, do I think I've got them right, cos and sine? Well, look at something at 30 degrees. Would you expect the y component or the x component to be bigger? Just look at the drawing. Is the y component or the x component bigger?
The y.
Yeah, and guess what? The y component's bigger, so we're good start. I mean, it's very easy to mix these up. You catch me on it, because I could do it too. So Fx equals F cos, it would be adjacent, cos 29, and Fy equals F sine 29, and TAX equals TA cos 38. And TAY equals TA sine 38. And for those of you who are sitting there going, why did I use sine for my y's for force and sorry folks, real life happens. When I use sine for my y's, for my F and my TA, and I used cos for my y in my TB, and that is because if you go back to the drawing, the TB is, the angle for TB is given with respect to the vertical. The angle for both force and TA is given with respect to the horizontal. So you would expect to be using the opposite here. Okay, those are just things I'm throwing out while I'm doing it, because those are the things that are really associated with what we've done in this course. So let's go with this sum of forces in the x direction. And that's going to equal TBX. Well, that's negative, because you can see it's pointing in a negative x direction. So minus 40 newtons. And TAX is also going in a negative direction. TA sine 38. Plus, because you can see FX is actually going in a positive direction. So it's positive plus F sine 29. Or sorry, I'm doing X's. I apologize. See, it's so easy to do. I'm doing X's, and X's are cos for these other two. TA cos 38 plus F cos 29 equals 0. Now, I could rearrange this and have everything in terms of cos. So, sorry, not in terms of cos, and everything in terms of F. I could choose F or TA. I have two unknowns in this equation. Actually, let's get the two. Sum of forces in the y direction is going to equal negative 69.28, because again, it's pointing down. Plus, because force is pushing up, the F force is pushing up, is F sine 29 plus, and again, TA is also pushing up, TA sine 38. That equals 0. Okay, so I have two equations and two unknowns. My two unknowns are F and TA, and I have my X and my Y equations of equilibrium. So if you have two equations and two unknowns, you can solve it. So this is the point. At this point in time, this is all I would ever ask of you in this class. But if you wanted to solve it, and that's fine. So we need to do this. From the X equation, we can see that F equals 40 plus TA cos 38, all divided by cos 29. And from the second equation, Fy, I could see that TA equals 69.28 minus F sine 29, all divided by sine 38. I can now substitute this guy into this guy, and I would have TA equals 69.28 minus 40 plus TA cos 38, all divided by cos 29, all times sine 29, and all of that would be divided by sine 38. So this is where I tell you, I'm not going to solve it. This will give you the answer. But understand that it's at this point in time, it's, and that's going to, well, yeah, TA equals. The only unknown you have here now is TA, so you can solve for it. There's going to be a lot of individual factors. You're going to have 69.28 divided by sine 38. You're going to have 40 times sine 29 divided by sine 38, and you're going to have to make sure you have a negative here and a negative in front of this other one. This one is going to be TA times cos 38 times sine 29 divided by cos 29 divided by sine 38. So you're going to end up with 4, because you have one over here, individual things that you're going to, 2 of them will have 2 TAs in them, 2 of them won't, and you'll be able to solve for TA. Again, it's not understanding equilibrium. It's not understanding how to take vectors and put them into, split them into their 2 components. It is, at this point, almost housekeeping, making sure you don't lose track of various values. And that's how you solve it. Any questions on that?
Thank you, Professor Moore. That clears it up a lot.
Good. Any other questions, Nicholas, or is that? Yep, good. Anybody else have a
Yeah,
question?
that was it.
Any other questions? Well, oops.
Can you tell any typical mistakes in midterm 2?
Not really. I mean, off the top of my head, no. I have to say the one thing with the digital exam, you're a little more separated from it. Okay, I have some information on the final, not everything. I don't have the timing yet. I want to make sure I get that relatively set. It will be, again, a mixture of types of questions, ones where you will have to calculate and ones where you, that will be multiple choice. One thing that I want you all to be aware of, and it's kind of important, is that, and you are probably seeing this in other courses. It is not 9 a.m. Yeah, not 9 a.m. Yes, it is 9 a.m., but it's not 9 a.m. It's April 23rd if you're in section M, it's 9:05, and if you're in section N, it's 9:10. They're trying to have some of the larger core courses not start right at 9 o'clock because so when I say it's not 9, it's not 9 exactly. It is 9, but it's not 9 exactly. And the reason is they're trying to stagger the starts a bit, so not everybody starts at the same times, which is a little heavier on the IT. So they've taken some of the big core courses, and this is one of our, yeah, it's like a 5-minute difference. Sorry, it's still a first thing in the morning, but it's a 5-minute difference. And so when you see the exams, when I finally release the exam so you can see it, you'll see one for M and one for N. And one will start at 9:05 and one will start at 9:10. I assume that you're seeing that in some of the other classes too. That I will post that. I have always posted, but I post closer to it because I want to, if I post it now and I decide that I might want to pull out a one or something like that, it's harder to do. So I'm going to hold off on doing that for now, but I will post it closer to. It is fully cumulative. It includes the whole course. Absolutely includes the whole course. And if you look back to the first day, it says everything's cumulative. And I'm not even going to try and split out to 30% and 20% and 50%, because it's not easy, it's almost impossible to do. We did a problem this morning where it was an angular momentum problem, which, and of course, angular momentum. We did that in the last couple of lectures. But you needed to calculate angular velocity in order to calculate it. We did angular velocity way back, like in the second week of classes. So, and force equals mass times acceleration. Acceleration was early on in this course, but you have to do it. So the point being that I don't give breakdowns because it's all integrated. It all builds on itself, and it's fully cumulative because of that also. Yes, we are going to have more tutorials. At this point, I'm thinking of staying with the Tuesday time frame. And yes, I totally do. And this is just a more efficient way of doing office hours for people who have questions, because everybody has questions and you can all see them, and we can spend more time on them. If do I know when they'll make it? Well, do let me give it a chance to look at them. I will try to. They'll be available this week. Okay, I'm going to Amos.
Yeah, it's just a concept with the stability. Let's say there's like a box, and then you're trying to create a torque to get unstable.
Yeah. You're trying to tip it over.
Yeah, tip it over. So trying to visualize it, I can understand that if you were pushing at the top, it's easier to cause a tilt.
Yeah.
any reason that you can't like angle it from the bottom to cause a tilt as well? Like it's below the horizontal. It's almost like a lift. Like
A lift would do it too. A
Yeah.
lift would do it too. It's usually not considered in the stability point, because if your goal is to maintain balance, then chances are you're not going to, like, if you're looking at a human, for example, you're not going to necessarily be pulling up on the front, but you could be. And yes, it will create, anything that will create a torque around will make it more unstable.
All right, thank you.
And yes, there will be a midterm 2 review. I'm just setting that up with the TAs. I'm going to stop recording here if nobody has a question.